Hi, everyone. I'm glad to be here. Thank you for coming to my presentation. I will speak about privacy and anonymity in blockchain. So let's start from who I am. I'm working at Canadian Institute for Cybersecurity. I'm a researcher, and currently I'm involved in 3 projects. It's about anonymity in blockchain. Next one, medical devices, security assessment, and I'm also working on Android software forensics. I'm doing also my PhD at UNB. I'm working in machine learning techniques for attributing the source code to specific author. So, like, I'm trying to answer the question, who wrote this code? By exploring the features in the source code. Previously, I was a cryptography researcher at Swiss Federal Institute of Technology in Lausanne, and I worked in cryptanalysis of the block ciphers and elliptic of cryptography. So I have like background in cryptography before joining cybersecurity. I will speak about blockchain as a new technology of trust, and I will cover a little bit the characteristics of the blockchain, the main attacks and security issues. Then I will speak about real-world blockchain use cases. Also, I will cover one of the main applications of blockchain. It's a smart contract, and I will explore like attacks on the Ethereum smart contracts. Also, I will speak about my research, which is I'm doing in CIC. It's about how we can attribute the author of a smart contract by analyzing the features in smart contract like code. What is trust? I'm thinking about trust as a foundation of every business relationships. So success is built on it, and it's all about how we care about our business networks. In our business relationships, we also have intermediaries who build the trust and who should have our trust. For example, intermediaries can be bank, yes. They care about if we are dealing with correct counterparties or our transactions with correct amounts. For example, we employ lawyers to be able to check that our products are not illegally distributed or copied. So this is intermediaries. They are very helpful, but they take our time and money. How we can create better, yeah? How we can put two business, for example, parties to communicate directly without the need of the intermediaries. Blockchain, it's a new technology of trust. Blockchain it's a goal to change the current economy to decentralized one, which is more secure and reliable. I'm thinking about the technology will actually create a new way that we are selling or buying products and also interacting with government. Let's see how blockchain works. For example, somebody requests a transaction. This requested transaction is broadcast to the network of the computers called nodes, and it's verified, each transaction verified by using a cryptographic algorithm. Then verified transaction is added to the block to existing blockchain, and that's all. Transaction is verified. Blockchain has multiple characteristics. For example, here there are 10 characteristics. It's decentralized, distributed, cryptographically secured. Let's explore each characteristic separately. Decentralized and distributed. As you know, that the traditional approach is to use the client-server architecture. we are storing our data in these columns and rows in multiple tables, and we have a unique key to access this data. Yes. So, for example, if client wants to access the data, he needs a credential to be able to communicate with the server. But this creates problems, very serious problems, because if hacker want to modify, change our data, he will attack the server. Yes, and we rely only on one server. It's very easy to attack. But we can do better is to use the distributed architecture. So in the distributed architecture, data stored on every node in the network. So to be able that hackers succeed in this modifying, changing the data, he needs to change in every node, and it's more time consuming with the client server architecture. So another feature of blockchain is transparent. You can see full transaction history. For example, here it's a screenshot of the blockchain explorer where you can find like all the blocks were created, by whom were these blocks are created, and the size of each block, time also. If you go further, for example, you can see how many transactions was in this block. Actually, transactions, the number of transactions depended on the size of the block. So it's approximately 250 bytes, the size. So also we can see the transaction fees, height, receive time, difficulty, size. Yes, transaction you can see, you cannot be able to identify the person. Yes, like who requests this transaction, but you can see only the public key of this person or public address on the blockchain. So here you can see the time of the transactions. You can see from whom to where this transaction was transferred. So blockchain is pseudo-anonymous. Somebody says that it's anonymous, but no, it's pseudo-anonymous because we can see clearly all the transaction history, but we cannot link that identity of the person who created this transaction. But as you can see here, for example, we can identify IP address of the person who created this transaction. So this has actually created some three main vulnerabilities on the blockchain pseudo-anonymity. So the first one is, yes, we can see the IP address in clear. So we can do, for example, DOS attack on this IP address to be able to deny of service this particular node. But you can say, for example, yeah, we can use a virtual private network or Tor, yeah, to be able to anonymize this traffic. It has also some limitations, such techniques. Another one, why we actually can see this IP address? Because nodes in the blockchain, they communicate between each other by unencrypted TSP. So that's why we can see this IP address. Then we can create a transaction graph analysis, for example, to explore all this graph from where to where money goes, and also link addresses to real-world identity. How we can do it? By using, for example, if person bought some bitcoins, yes, or on somewhere, he can, for example, leave the name of the or email address. Yes, so we can link this IP address to the name or email of that person if it's real, or some online platform if he left some traces there. So actually, it's not bad because, yes, last year was the race of the ransomware. Everybody knows that ransomware can encrypt all the data on your computer and you need to pay ransom, yes, to be able to access your files. But even if you pay the ransom, like I saw statistics, companies, 30% of companies, they didn't receive their data back. So what is good, for example, in ransomware connected to blockchain, that ransomware you need to pay by bitcoins. So we can trace these Bitcoins wallets, for example, in blockchain by using, we can create the data set. For example, in our institute, we did some research in this. We created the data set of the ransomware. We used static and dynamic analysis to be able to extract the payment side and the wallet, Bitcoin wallet of this ransomware. And we were able to see some interesting activities there. Actually, a lot of research was done about anonymity of Bitcoins and analyzing this IP addresses flow, yes, or like from specific source. Also, a lot of research was done by understanding how money go, yes, like by analyzing, for example, Bitcoin user network. Bitcoin, they were created, you can see, actually from 2009. All this transaction, and here researchers, for example, from University of California, they showed they cluster all the network of Bitcoin network by groups such as bank exchanges, vendors, mining pools, and for example, here edge, it's most you need like you can create edge if there are more than 200 transactions between these nodes. So here you can see by blue, it's indicated mining pools. By red, it's vendors. Green indicated wallets. These clusters. And they actually made the conclusion that a lot of amount of this transaction was for gambling. Online gambling. There is a lot of nice software to use to be able to trace this activity, to explore this traffic and everything. And for example, one of the software I played with is chain analysis. It gives you opportunity to look to create these clusters and to look from whom and to whom the Bitcoins was sent, and to see the interesting analysis, to make interesting analysis there. Okay, yeah, we can trace it. For example, banks who are using blockchain, it's very difficult because they need to somehow to encrypt this data as it's very sensitive for them. So for this purpose, you can, for example, use private blockchain. It requires they give only access for members who could be co-founders, and semi-private, for example, qualified users only can access this blockchain. And of course, you see the difference of the number of users. For example, if public is millions, but with private or semi-private, it's only dozens to few hundreds and hundreds to thousands. Another feature which is very important is immutable and unmodified. For example, if hacker wanted to modify some data, he should modify it in every block. Because for data integrity, they use hashing, and they hash they use a Merkle tree to be able to hash the data. For example, every leaf is a hash of the transaction, and every non-leaf node is a hash of the previous hashes. So we also can see here that the block header has previous root hash, previous hash, and very important time stamp. Because every block should has a chronological order to be able to also it makes protection of the data integrity. So another feature is cryptographically secured. So yes, I was talking about hashes to protect data integrity. Then public key cryptography, you have public and private key to be able to identify the person. And also they use public digital signature. So digital signature, they use elliptic curve algorithm instead of the maybe famous RSA algorithm, because in elliptic curve cryptography, the length of the key is much smaller than in Rivest-Shamir-Adamar algorithm. And the security of both algorithms are almost the same. They relied on this mathematical problem, which is very hard to solve. Consensus driving is another feature of the blockchain. It's relied on proof of work. So to be able to create the block, you will need the transaction details, signature of the parties, hash of the previous block, but also unknown nonce. So why they make it? Like every single block can create only in every 10 minutes. They make it because to make resilience of the DOS attack on this. So, for example, to be able to obtain these nonce, miners, which is a node who mining the blocks, they need to solve mathematical problem, which is very hard to solve, but very easy to verify. What is this problem? It's they need to find the nonce, which is after hashing, they produce a number with a certain number of zeros. So that's why here, like now, we have a global cryptocurrency mining site. And you can see here, for example, on the map that China has 111 megawatts that use it to mine the cryptocurrency. Yes, cryptocurrency. And in Canada, we have, for example, 18 megawatts. So actually, this mining, yes, it's very power consuming, but it's not only power consuming, but they create, sorry, this is, I will come back, but they create the attacks on the devices or mobile devices or computers. So, for example, cryptojacking and crypto mining. If last year was the year of the ransomware, this year is a crypto mining campaign. This malware can not only, for example, as we saw with ransomware, it encrypts your data, yes, and you need to pay something. But they know, no, you don't need to pay or anything else. They just, this malware will just silently sit on your device and mine cryptocurrency for hackers. So there is an increase of the CPU usage, and the device execute more slowly in this scenario. So proof of work, yes, it's good, but we need something better. That's why, for example, for smart contracts, they use proof of stake. So proof of stake, they don't require this mining of cryptocurrency. They create a new block by choosing it in the deterministic way. So depending it's on wealth, yes, of this nodes, which is participated in the blockchain. So it's more efficient. It doesn't take so much time to create a new block. So now let's speak about attacks on the blockchain. So as I was telling about denial of service attack, yes, majority attack. Majority attack, if for example, attacker can occupy more than 51% of the nodes in the blockchain, it can, for example, modify all the transactions. But this attack is very hard to achieve because, as you know, that the blockchain, the network is growing fast, and to be able to occupy each of the node in the blockchain, it's very hard. Also, Sybil attack. Sybil attack is an attack where attacker control the nodes in the system. It can be part of the majority attack. Double spend attack. For example, if let's say we are buying, I don't know, sandwich, yes, for $10. We cannot use this $10 to buy something else, let's say poutine. But the problem is in blockchain, we can do this. And quantum computing. Yes, there is opinion that when it will exist, yes, it will hack all the cryptography which is relied on the mathematical problem. For example, Rivest, Sharman, Adaman is relied on the factorization of the big integers. Yes, elliptic curve cryptography, logarithm problem. So if we have this quantum computing, we can easily solve this problem. But I think that this is not an attack right now, because researchers can easily switch from public key cryptography, for example, to lattice-based, which is resilient to quantum computing. We can see a lot of use cases of the blockchain. So it's ranging from authorship to data management, government, enterprise. For example, healthcare, how it uses. MedRec is a blockchain platform where patients' data can be stored or accessed across different organizations. And it's in secure way because medical data is very sensitive. Like your all medical records, name, addresses, like everything. Yes, and it's if you use blockchain, it's more secure way to store this data and access. Also authorship, for example, copyright platform where photographers can protect their images without paying any fees. So this is just a small part of these examples. If you're interested to look more on this, you can follow the link. So smart contract. Smart contract is one of the main these applications of blockchain. So, for example, if somebody's selling house, yes, he just can create a contract by using a code. He can write the code which is identifies the contract, and he can write everything like price, yes, or some another options. If, for example, I receive this money, yes, no, the house will be sold to this person. If I don't, like, you know, it's everything, it's algorithm, yes? You can easily write it in the code. So why not to make it? There are blockchains where you can process smart contracts. Actually, I was very surprised to find that on Bitcoin, you also can process smart contracts. But Bitcoin, they don't have Turing complete language. Where you can easily write this contract. So it becomes more harder to work on this platform. For example, sidechains, NXT, and Ethereum. Ethereum is one of the most popular one. It has a Turing complete language, and you can easily write there. Also, you need to pay for computing power in Ethers. Tokens. So idea was, you know this guy, Vitalik Buterin, who is a Canadian and Russian programmer. He actually published a white paper where he explained everything about smart contract and idea how to make it. Yes, how to change this way of selling or buying. So it was in January 2014. And what's the difference? What's the main difference between Bitcoin and smart contracts? That contract, we have now contract account and non-contract account. So in contract account, we have nonce, balance, also code and storage. Non-contract account, we have only nonce and balance. Contract bytecode is looking like this, and it's storing on the blockchain. If we, for example, disassemble them, we can turn it to the opcode view. And for example, if we comparing contract code of the just regular code, yes, in contract code we have gas. So attacker, for example, will try to create some function which is running like forever, yes? But in contract code, you cannot make it because if you want to use specific function, you need to pay gas. So for example, you want to load in, you need to pay 200 gas, creating 3,200 gas. And you can see the block gas limit. So contract you can write in a language such as Solidity. It's one of the most popular language. Also LLL. So it's like, I don't know, low-level language, lovely little language, Lisp-like language, or lovely little low-level Lisp-like language. Like everybody speaks about it differently. So also Serpent. So Serpent, actually it's a Vitalik created this language specifically for users who doesn't know like very well programming, and it should be like very easy to program the contract. But the problem is this Serpent is not fully created yet. Like it's better not to use because it's have a lot of critical problems there. SRSCA. So as we saw, for example, for blockchain, we have Explorer, yes? We can have Explorer for Ethereum smart contracts, where you can see the Ethereum balance, number of transactions, contract creator, address. Like you can see here, very it's very visible. So also we can see the contract code. We can switch to opcode view or find similar contracts. The interesting thing that smart contract, which is Ethereum, they have Ethereum virtual machine. So we cannot, for example, from bytecode view, we cannot switch on the source code. We cannot, because it's Ethereum virtual machine, it's like, it's obfuscated, the source code. It's for protection, additional protection. Let's say in Bitcoin, we have IP addresses. Yes, we can easily see all these IP addresses. But in smart contracts, we cannot see IP addresses of the creator because of this protection also virtual machine. As you can read, opcode visible and runnable on the whole blockchain could be published by author, and everyone can verify the code against the opcode. So this is crucial. Then a lot of attacks made already in Ethereum smart contracts. So think about, like, let's say code on Java. Yes, you can write code and then come back and fix, like check on vulnerabilities. But with Solidity or just usual smart contract, you cannot make it because you published already on blockchain and you cannot modify your smart contract. So it's very important to check before publishing. It creates a lot of vulnerabilities on the smart code. For example, on Solidity level, Ethereum virtual machine, and blockchain. So everybody, maybe of you, knows about DAO attack. It was an organization which is created, like you can invest in them and buy some part of the smart contract. So it raises, like after this, it raises 130 millions. And you can see this Ethereum chart. It's like increased so much. And then this chart is just dropped. So what happened? It's because of the re-entry attack. How I told that the code, it should be checked. Like a lot of now, I saw like on like on YouTube and everything. There are a lot of, you can know about vulnerabilities in the code and how to protect your code against them. So these smart contract creators, they should know this before the publishing. For example, re-entry attack. Attacker can easily not only withdraw your like one time, yes, from your account, but it can keep withdraw multiple times, like recursively, by using a split function. So now let's speak about like attack which is we are proposing in CIC on privacy anonymity of smart contract creator. So we have a problem, a research problem. For example, in Bitcoin, yes, we can create this, we can do cluster analysis by using IP addresses and to link to the person, yes, but in smart contract we cannot. We don't have this IP address in clear. So what we can do, okay, we have bytecode, we can have source code, if it's published in Ethereum Explorer, and how we can attribute it to the specific person. We are using authorship attribution method. So this method is, it uses machine learning approaches to be able to extract all the features in the source code or bytecode, and that then attribute to specific person. Because like there are two types of people, yes? It's only one feature. Okay, think about, it's only bracket style. But in authorship attribution, we have like more than 1,000 of features. And we can, with, for example, 93% identify of this source code creator. So this is research, yes, this is academia. But I saw some work was made and presented at Black Hat. They use this technique in malware analysis on the top of the tools they use. And they were able to identify the malware, to say, like, for example, whom, like, what country made this? Please don't like blame Russia on everything. Let's at first like analyze, okay? Extract these features. And actually, in my PhD, I'm working on checking if these attribution techniques can be circumvented by attackers. For example, let's say if we add some Russian comments or imitate somebody, yes, or hide the identity, it will be attributed to Russia, yes? Or like we need to think big about this that attackers they're very smart actually, and they can easily imitate somebody or hide their identity. So we need more features to be able to say in 100% that it was from this source or that source. Yeah. So description feature set which we are using in this research. It's term frequency unigrams. We tokenize all this code by unigrams and explore the count term frequency of this. It's also like, think about if you write something, not code, let's say letter, yes, and you use like a lot of and in this letter. Yeah, it like you can easily attribute to this person, yes? It's like a style. It's writing style or coding style. Or in coding style, let's see, like somebody uses for loop, somebody uses while loop, yes? So this is very, depends on the person. Also, we are analyzing abstract syntax tree features. So we derived it from the abstract syntax tree. We're using bigrams. Like, for example, we have class, import declaration, then class declaration, yes, in the abstract syntax tree, and then like name declaration, method declaration. So we actually explore if a person put a name declaration before a method declaration or in the method declaration. So by using bigrams, you can actually easy to track this. And layout features. Layout features, yes. Maybe you will say me that where did you see that malware has their source code. It's all go in binary, yes? But if it has, we can, for example, see the comments, yes, like language of these comments, type of brackets, spaces, tabs. Also bytecode, yes, idioms we use, control flow graphlets, super graphlets, lib calls, and grams. Results is initial results. So we created our data set by using SRScan. It's like Explorer, where you can actually extract all the bytecode and source code, if there is a source code. We are using features, tone frequency unigrams. We really wanted to try it first very easily extracted because like Solidity, they don't have this, for example, in every language, to extract the control flow graph features is much more harder than tone frequency unigrams. So that's why we decided to make analysis at first on easy extracted features. Number of features you can see, and we use also informational gain approach to be able to decrease the number because a neural network, for example, will run forever on this number of features. We use classifier. We tried like everything from tree and SVN and we be able to see that random words perform better. So in control-sourced code, we get 88% accuracy by identifying the source code of the contract code to specific address. Because we can check it, yes? Like when we create in the data set, we have these public keys, and we can check if the contract code belong to another person. Like we create in training data set testing, like every, if people here working in machine learning, they know this. In contract opcode, similar, we extracted tone frequency unigrams, and we get much less number of features because how I say is that like in source code, we can use like comments and everything. But in opcode, we have lack of these features. That's why we received much less accuracy, 75% only. So conclusion and future work, we'd like to extend this research work, and we want to extract not only tone frequency unigrams, but also abstract syntax tree and control flow graph features. Also, we'd like to cluster all the contracts by they are not like public keys or accounts, but also to real identity. So by analyzing the coding style, for example, if we see the coding style is similar to some certain number of public keys, we can create this group. And it will be very interesting to see, like for example, Ethereum, you can create, in blockchain actually, you can create how many keys you want. Yes, you can create like every key for each transaction. But it's very interesting to see if we can, by using coding style, by using authorship attribution techniques, to link this contract to the identity. How many, for example, identity created contracts, yes, and to analyze the statistics. So that's it. Thank you so much for your attention. I'm happy to answer questions if you have. Yeah.
Why it matters?
Attribution, for example, you want to know the source of the attack, okay? For example, we have a lot of attacks now, yes? We can create, let's say, new antivirus and firewalls, but every malware has a signature, yes? We will create this antivirus based on this signature. But if malware changed, yes, like a little bit it changed and signature will be different. And antivirus cannot already resist by this malware attack. In attribution, we rely on the not what is malware, yes, and how it interact, like, but we rely on who wrote this malware. Because if somebody started to write malware, it will continue, yes, but it will have the specific features of this identity of the person. So we can look on the identity of the person rather than characteristics of the malware. So I think that actually attribution, like if we can add it to antivirus, for example, it will become more resistant. And I saw the statistics of this malware, you know, and every year it's growing so fast. It means like we are doing something wrong with this. Why it's growing? Maybe we can focus our area to attribution more. Thank you so much.